Okay, so in this video, I'm going to introduce the idea of um, representing solutions of the systems of the differential equations with vector fields. And so this is going to be kind of how to generate a vector field, at least how it is generated. And so to do that, though, we need to talk a little bit about vector valued functions. Vector valued functions. So a vector valued function is a function that's based on a vector rather than an equation. Of course, the vector could have equations within as the terms of the vector. So what we're going to do is we're going to take, so if we're looking for solutions to this equation, we're going to create a solution that's made up of, that's a vector valued solution that is, so let's say P of t is my solution. P of t is equal to the vector r of t, f of t. Sorry. So again, that means r of t would be the solution to this equation. Well, they actually both are solutions. So in other words, we're saying if we plug in r of t there, and take the derivative there, and plug f of t in here, let's use colors. This arrows are lame. Okay, so we're saying, so here's r of t. So that means it would go there, 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 and there. Here's f of t. That would go there, 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 and there. So what we're saying is that r of t and f of t are the solutions, or they together is the solution to this differential system of differential equations. So that means that we could call this the P, the solutions vector. Okay, or vector value function, I mean. Okay, so if we know that this is true, then we could also do this. We could take the derivative of P of t. Of course, you can take the derivative of vector valued function, which would give you dr dt and df dt. So this right here represents the derivative of the vector valued function, which is the solution to this differential equation. And of course, we know what dr dt and df dt is, so we can rewrite db dt as, and we'll have to make this a little bigger, 2r minus 1.2 rf and negative f plus 0.9 rf. So that would be, and of course this just came from the original function, in case you didn't remember that, the original differential equations. You can see that we just replaced dr dt with what this says it is, and df dt with what that says it is. Okay. Now, so what the vector field does is it assigns a vector to each point in the field, very similar to the slope fields we had before. So if we take a nice big plane, and in this plane we're going to call this the r, or the rabbit axis, and this is the f, or the fox axis. And if we pick some random point like 2, 1, and put a little dot there, so we want to know that if the rabbit population was 2 and the fox population was 1, what would these differential equations, the solutions of these differential equations, look like? That's what we're trying to get at, right? So so in each point, we can assign a vector to that point. That's what this thing here is doing to me, and that vector would represent the derivative of the solution, which would basically be a directional vector for the solution. So let's do this. So in other words, I would want to know what So let's just make this to cut back on the rotation. We'll call this v of t. No, we'll call this v of some point. Okay, because now the derivative is being represented as a vector. So, for example, if we want to know what it is at this point, we would say v of 2, 1, because the rabbit population is 2, the fox population is 1. So we're plugging it into this vector valued function, and we could calculate a vector. So that, maybe I should make a little bit more room there. That would be 2 times 2 minus 1.2 times 2 times 1. And that would be negative 1 plus 0.9 times 2 times 1, which of course would give me 1.6 and 0.8. So now we have a vector that represents the direction of the solution at that point. So we could go up here and we could draw a vector. Looks like it's going in the rabbit direction, 1.6, so that'd be 1.6-ish. And we're going in the fox direction, 0.8-ish, so that'd be right about there. So that vector is going to be like that. So that is the direction, that gives us a kind of a directional idea of what's happening. So it looks like at that point, the rabbit population is growing and the fox population is growing, but the rabbit population is growing a little faster. That's what that vector is telling us, if that makes sense. Because this vector in this case is really comparing the growth rates of the two populations. So then we could calculate another one, like for example, what's the vector evaluated at 1, 1, for example. So that would be, if we again plug it into the same formula, we would get the vector 0.8 and negative 0.1. That's interesting. We're not that far away. We're over here at 1, 1. And the vector is very different, isn't it? So at that point, we're going 0.8 in the rabbit direction, but negative 0.1 in the, so you can see right about there. We blow this up a little bit. That was way too small. Let's do this again. We'll go here we're going to go 8 and negative 1, so right about there. So you can see that if we keep doing this, we're going to get pretty crowded with with vectors all over the place, and especially if these vectors are longer, right? These are only 1.6 and 0.8 and so forth. But you could imagine possibly a vector that's you could imagine possibly a vector like this, and then you're going to have this super long vector, right? So, but you can also tell that if we were able to draw all these vectors in, and you were able to see what's going on, this would give you a very good idea of how to evaluate what the solution to this system of differential equation looks like. But the problem is, again, with these full-length vectors, it can be hard to discern where the vector's pointing, because if you had even if you just had one at each point, you can see that these things are going to start overlapping each other. So generally what they'll do with a vector field is they'll turn it into a directional field, which means the difference is that we make all the vectors the same length by turning them into unit vectors, or small, even smaller than that. And what that does is it takes away a little bit of information, because remember, the way vectors work is the length gives us their magnitude, and where they're pointing gives us a direction. So if we just cut them down to all be in the same size, we won't be aware of the magnitude of each vector anymore, but we will know the direction of the vector. So that's how, if you have the full-length vectors, we call that a vector field. If we shrink them down to be all the same size, we call that a directional field. So that's the idea of the vector field, kind of how it's produced. There's another video following this one by a different character. I don't remember his name, but that will talk a little bit more about this idea that I was just talking about of having converting the long vectors into vectors of the same length. And he does this cool thing where he shows the different colors could mean different lengths of vectors. But okay, hopefully this is helpful.